Hey, what's going on, y'all? So today we are going to be talking about the BOP challenge, and this is something I've been really interested in for the past couple of months, and did not know the learning curve to actually be able to compete in this sort of benchmarking challenge was so steep. So really here, what I'm just trying to do is just share my knowledge and have an area where we could, have a discussion on these sort of topics. And I found it interesting. So part of the project, just sharing some of the interesting findings and descriptions from the journey through this pose estimation project. So essentially, what do we refer to by the 6D pose estimation problem? So here, we're really just referring to given an image, usually in the form of like an RGB or RGBD channel, we want to estimate the 3D orientation and the 3D position of an object relative to the camera. And that camera coordinate system is something that I'll definitely have another post to talk about separately. So what is BOP? BOP is essentially benchmarking schematic for just basically standardizing how we approach specific data sets and evaluations for 6D object pose estimation. And essentially, BOP provides a unified set of data sets and also provides an online platform which facilitates how the benchmarking challenge is hosted, it's an online evaluation system. And there are a couple different metrics that are being used, a couple in the past, but some recently that we're planning on discussing here in this discussion, primarily on the visible surface disparity, VSD metric, and we'll go into that a little bit at a high level a little bit later. So essentially what BOP really is here to address is, given an object pose, how are we able to recover how are we able to recover that pose of that object only considering the six-dimensional view of the object pose? And there's a series of different methods and algorithms that we typically utilize in order to be able to recover that specifically at a more instance level. So if there are several objects laid out, if there are several objects laid out per instance of each of those objects, how do we then recover that six-dimensional pose? So really what this challenge is here to do is be able to enhance the approach of being able to estimate those six-dimensional poses. And there's several different challenges that within this BOP benchmarking challenge has in terms of various applications. So for robotics or manufacturing, pose estimations really do need to be particularly accurate, especially as you're really referring to machinery or some sort of robotics trying to grasp objects and move them to a different location. So they really, my goal hasn't really been focused on robotics, but understanding that sort of importance on how various accuracy and evaluation measures that we use to determine how accurate these estimations are, with that kind of understanding in our back pocket of understanding, okay, the machine could be grasping at this rubber ducky, for example, and what sort of other requirements should we keep in mind as we're going through this challenge and completing the estimation. So here is just basically a high level overview of just, the key objective here. And we'll kind of go into a little bit more depth on specific aspects in relation to it, the challenge. So this is, so with the BOP challenge, there are a series of different data sets. And for the fall 2020, BOP challenge, there's, I believe, 8 data sets that has been provided, which are kind of deemed as like those core data sets. And all of these data sets range for what sort of occlusion sort of focus that they're really focusing on in that data set versus lighting, transparent objects versus, just dealing with lower complexity as far as objects goes, or whether objects have more of a continuous or discrete sort of shape. So each of these sort of data sets really provide, and you can kind of see here where this is like the RGB image here, and then we get the depth view of it as well, because depth does play a crucial role into being able to look into that additional dimension to get that z-axis and be able to interpret how far the depth perspective in relation to the camera coordinate system these objects are being located. And usually those are not very common, and but the BOP group has done a pretty good job on providing necessary annotations with those ground truth to really just lower the bar on, okay, we already have data sets available, very much in the same way you have like the COCO data sets and other sort of public data sets. This one specifically just focused on, okay, now we're getting into the realm of 3D object detection. Let's start working on being able to baseline some of those practices and compare methods. Okay, so with the understanding that, okay, the given task that we're really trying to focus on here is to estimate or be able to estimate the 60 pose of a variety number of instances of a variety number of objects, and really in all of that is going to be in one image. So there really isn't much that we can do with when dealing with like a video series where we can kind of infer object locations from prior scenes to other scenes. However, that sort of scene methodology is used here, especially as you're able to do variations with, depending on how the data set's collected, on how you're able to render certain objects for image collection. So given that, we have a lot of different objects that could be, one or multiple in a given image, and we're trying to do inference off of that pose estimation for that single image and be able to come up with a list of, okay, here are the number of instances provided for each of those images. Now we kind of take into consideration, okay, since now we have estimated those poses, how, what metric are we going to use to determine that accuracy? And the BOP challenge has provided a set of different evaluation protocols for the 2020 challenge. And this fall, there are 3 specific ones that are then averaged together as a kind of a map sort of view of that. Here, we're just going to focus on one of the 3 metrics. I'll give a description of the others. It's just I wanted to keep this one a little bit higher level and not get too much into the weeds. We'll have another video that will definitely go into a little bit more detail on some of these evaluation metrics because I struggled with the other 2 metrics. But this one, I think I got a pretty good grasp on the intuition, so I can share it with y'all, but definitely feel free to leave a comment or feedback if there are other ways that I could have presented this topic. So here, what we have here is basically one of the 3 evaluation metrics. And really when we're talking about evaluation metrics, we're really only concerned with rigid objects that are being considered. And here, since one of the outputs in which is coming out from the model, and there's a couple other videos below which we discuss about some of the methods that we're utilizing during this challenge, is that we're able to provide what sort of error rate we see for a given estimated pose. So how confident we are is in terms of that accuracy of that pose. And one of those metrics that we're tasked with being evaluated on as far as the error of our projected pose is that we look at the VSD, which is the visible surface disparity. And with this measure, it basically calculates the error over the visible part of the model surface. So here, we have a suite of different images here, and essentially when we are first starting off, okay, we've done training, and now we're looking to test, evaluate how well we train the model. So basically we have, images that we have not seen yet. We did not use one pixel. Requirement for this challenge is that you can't use any of those pixels, but they do give you those test images. So we have a set of test images, and each of them we already know, what those ground truths are. So we really just start off with these test images here. Then we'll be able to go through them. Utilize the model to be able to, one, perform the detection for the object, and then two, be able to estimate the various poses for each of the various object instances in a given image. And this is the second section here, which is from that RGB image and the depth image from the test image, we then are able to provide our estimated depth and pose, which provide the S hat as far as the depth image, and then the visibility as far as the V hat. And both of these are going to be, impacted as far as how we estimated the pose of those images there. And then finally, we have this third section of images here, which is the ground truth pose. And these are basically, S bar and V bar, very much similar to those, but these are just what we know is true. And essentially here, what we're trying to do is signify the distance, the image and the mask are, and then be able to calculate the visible surface disparity in terms of how far away our given pose estimates are in regards to, one, the pixel density, and well, actually, yeah, it is just the pixel density. So what we see here from the V bar are the mask. So in our estimated one, and this one's coming in blue here, we're really, so we know what the masks are, and the mask is just an accumulation of all the different pixels within what we know is to be true. So we basically remove the background and just have one solid set of pixels, which is an array of, okay, in this given image, here are the pixels that we have mapped to this given object. And basically, we're just calculating the distance here. And a bit of intuition here is, I guess what I think is a bit of intuition here is that the smaller this distance metric is. So you can kind of see here at the bottom here are the results from the visible surface disparity. So as it decreases, we can kind of get that sort of intuition that that the smaller the distance, the darker that pixel intensity is, which would indicate that that there is going to be overlap, and that we do have a higher rate of those pixels matching up to what the ground truth is. So I guess in short, or in other words, the pixels with unknown distances would be in the darkest color. So it would be more of like in shades of black. So what really took me a long time to kind of get this intuition, and I just finished training the model, so now I'm getting to utilizing some of these post estimation metrics. And what I really saw was that when we first start taking that individual image, RGB image here, and I think it's more specific that you can kind of see these indistinguishable poses, and that's really what the goal of this this metric is doing, is basically we're wanting to estimate, the consider if it's correct, and the darker it is, the more invisible the object is. So if we do have like a front view here, and we couldn't be able to estimate what that pose is for the coffee cup, because we couldn't really see, the handle part of the object. And I think, kind of going to this example here, where, we're able to see, okay, here are certain sections of the object, and it when we estimate the pose, we kind of get that sort of differentiation where we kind of see this sort of connector here and at the top. However, if we try to estimate it on, this object here, it's relatively unclear because, this sort of piece here and these sort of switches here are not visible. And when you have that sort of ambiguous view of what an object is very hard, or most likely impossible, to be able to correctly estimate that pose. So what we'll do there is then we would calculate, basically would compute this and basically calculate the error over the error over the union of the V bar, which is the ground truth pose here. And what this would give us is now we're able to basically match them up 1-to-1. So we know what the estimated one is and we know what the ground truth pose is. And essentially what we'll do here is be able to have a way to obtain the final estimated pixel value, which should be less than tau here, which usually it's going to be 0. 0 is going to just indicate those darker pixels, which are just going to be what's in the background. It's everything but the mask, because the masks are going to be whatever we have as far as the color objects. And these are the V bar and V hat. Those are the color objects, and the depth ones just only indicate the depth value. I guess just to note here, and I guess, yeah, you can kind of see as it gets higher and higher and higher, you can really see how the estimated and the ground truth really does shift. And a lot of it does have to do with the visibility of certain features within the object. So if there's certain parts occluded, just like we kind of talked about for this coffee cup here, it would get a really high score because we wouldn't be, like, there are pieces of that object that is not visible. And BOP, the group's provided a nice little SDK for computing or really handling a lot of these data sets. It was quite difficult at first to be able to start processing RGB with the depth images, and then there's tons of different methods that includes making sure that these are feature points, or establishing various key points, or putting this into some sort of cloud matrix. But the BOP provided a way to have a kit to render a lot of these objects in a much more standard manner. So there are, like I said, that this is just one of the 3 key evaluation metrics. There are 2 others which I just haven't had enough time to get into, so I'll just kind of give you the definition and high-level use of how I think it's being used. But I will do another video to provide some highlights on that specifically. So there's 2 other metrics in addition to this VSD, which really just provides an indicator of the visual surface parts of the object and identify which ones are not visible or visible. So next, what we have is basically we can so basically what we'll do next is we look at the maximum symmetric aware surface distance, which essentially measures the surface distance in 3D. This one's really much, I think it's more towards robotics, when, kind of what I was talking about, where, there's an arm that actually has to put a chip into a certain spot, or take something off the shelf and put it onto another shelf. This really helps with being able to put that pose function into a 3-dimensional space to be able to determine whether certain objects are symmetrical and not, and be able to get that maximum distance. And for a more surfaced 3D perspective. So instead of just doing the visible surfaces, this one's measuring the pose function for symmetry, for any sort of deviations in that surface and in a 3-dimensional space. And then finally, the last one is the maximum symmetry awareness projection distance, and that one is just a measure of distance on a more perceptual basis. So in the majority of methods that I've read, there's usually going to be some sort of P&P, perceive and project algorithm, which essentially enables the camera localization, or the camera intrinsic and extrinsic values, to be able to understand, okay, here is the line which the camera is viewing objects, and you're able to get that, you're able to utilize the dimensions of the camera, and then have, really an RGB image, instead of using that depth metric, to be able to provide that sort of measure, to be able to perceive some sort of deviations in how we are estimating that. And really, that all really comes down to how we're translating that Z component of that rigid body rigid object. And so I'll definitely do another video on camera intrinsic values and how we were able to estimate that Z value, because that one took quite some time, especially as I'm trying to utilize my own custom data set without having a depth camera, and be able to still infer or calculate what the depth value is. Because if you do not have that, it makes one, object tracking, but two, most importantly, the ability to do pose estimation very, very difficult. It's very, very difficult. So it was an interesting aspect for that. So just in summary, there are 3 key metrics that are utilized for the BOP challenge for this 2021. It is the BSD, which is the visible surface disparity one. This is the one that we just talked about here. There's 2 others, both in regards to the maximum symmetry. One is the maximum symmetry, maximum awareness surface density. And then the other one is the maximum symmetry awareness projection. And both of those are, like, all 3 of those are distance functions. One is just looking at, the visible surface disparity. The other one is looking at, from a 3D perspective, of the distance measured for the surface, derivations for how we're able to estimate in a 3D space. And then the third one is looking at the awareness projection. So utilizing more in a more, I would say, a more augmented reality sense, where we're estimating the Z translational component, which in essence we'll have to translate in all 3 of them. It's just that for this one, you don't always have that depth channel to be able to do it. And then just to really just sort of cap off, I thought that this was important to note that there's several key rules and requirements in order to participate in the challenge. One is, for training methods, you could create, you could generate your own images, or you could utilize the rendered images that they provide you. They also provide a really, really sweet repo, SDK, which is basically, you're able to re-implement how the rendered objects are for the actual data set that's being provided, or you can create extra ones. The second one is that you can't use, and this should be obvious, but just to iterate, you can't use test images, not a single pixel during training, not even the ground truth. So don't do that. That's cheating. And the third one is that all of the ground truth poses, especially for the test images, it is all estimations. So when looking at that score, it's more of a range and not a probability distribution. 4 is one that I understand why it is a rule, is because it will make very difficult to have a more standard evaluation, but something that I'm just looking forward to tuning on my own, which is number 4, is that you have to have a fixed set of hyperparameters, especially when you're doing your training and eval for all of the objects and data sets, which we'll see how, because I know that there's a lot of thresholds utilized specifically in those that have symmetric versus non-symmetric objects, and having a consistent one there, even when you do have a model per object, is interesting to understand why that they did it. It's just yeah, I may just experiment on my own on that one. And then also, there's a requirement for the final requirement is that you have to provide a documentation as well as the code that's utilized for participating in this challenge. So, and then finally, here's a link up here. This is where you're able to submit it and submit your to submit your results in. And essentially what you do is just you'll download the data sets, you'll do your training, modeling, do your eval, iterate, and then when you're satisfied with those results, very similar, it's very similar to like a Kaggle data set, your Kaggle competition. You just upload it, and they have a structured format in which you would upload those metrics in. You don't necessarily have to do all of these data sets. For me, this is really my first time going, and I'm probably just going to do one or two of the data sets that I've been able to download. So that's also fine. And then as far as like the test image here, there's a lot that are going with RGB or RGBD, and while those do have very strong benefits on itself, for the first time here, I'm probably just going to be doing RGB, just from the standpoint that I want to be able to create my own data set afterwards and be able to, I don't know, I really like the way that you're able to have now a 6D bounding box and be able to understand the pose and localization of specific objects. Mobile devices aren't really there yet, but it would be really sweet to be able to put it on a couple IoT devices or something like that. So, and in order to do that, I really don't want to buy a bunch of depth cameras to be able to do so. So right now I'm just trying to get my understanding on just RDB implementation. And I think that also has, for right now, a wider scalability, but obviously, even mobile devices now is going to be very, very common for these to start having depth cameras, and it should be easy to get in. So, like I said here, the highest AR score. So yeah, it's an average view of those three metrics. But yes, I will cap this video off here because it has went long enough. This is the benchmark for 6D object pose estimation. And for this challenge, as of this recording, it is due August 19th. I believe that they just updated the submission, so sometime next week. But yeah, I will talk with y'all later. See y'all in the comments.